Hi, my name is Brian, and I'm interviewing Kaushik Roy.
Hi, Brian. Good to be here.
Can you explain what the C-BRICS organization is and your role in it?
Okay. C-BRIC is the Center for Brain-Inspired Computing. It's actually one of the JUMP centers. JUMP stands for Joint University Microelectronics Program, which is funded by DARPA and 14 other industries. And in C-BRIC, which is the Center for Brain-Inspired Computing, we are developing sort of algorithms for autonomous intelligence. Looking at this entire stack, going all the way from algorithms, from sensors to algorithms, to also developing hardware that can implement some of these algorithms very efficiently.
Okay.
So to that effect, there are several universities involved. There are 9 universities, and there were about almost about 140 PhD students from these different universities involved. I direct the center. And as a part of this center at Purdue, there are almost 50 PhD students involved in the project, looking at either the algorithm side of things or the sensing side of things, or for AI hardware.
Okay. So I watched some of your previous talks, like your CVPR workshop talk, your nature talk. One thing that I noticed is that you mentioned a lot about SNNs, or spiking neural networks. Can you explain a little bit more about them and how they work?
Yeah. Certainly, deep learning certainly has made a huge amount of progress, right? And most of the networks that we use today, the artificial neural networks, they're certainly, weakly inspired by the brain. No question about it. Now, if you try to have more bio plausibility and say, hey, is it possible to use a neuron model which is more like what the brain does, so to say? And then you can potentially try to use the Hodgkin-Huxley model of the neuron, or more, the neurons which are sort of modeled in terms of what has been observed in the brain. So to that effect, one of the things that we've been looking at is the activation function to be more like a leaky integrating fire. So at the output of a neuron, then neuron has a membrane potential. When the inputs come in, it actually adds to the membrane potential, and the membrane potential goes up. But if it hasn't reached a threshold, it doesn't fire. But if we reach a particular threshold, then the neuron fires, and else it leaks. And it's leaking all the time. But if there are more inputs which are coming in, then the membrane potential goes up. If there are nothing coming in, the leak comes into picture. It leaks slowly. But beyond a certain point, when the threshold is reached, it actually fires. And the firing is sort of, you can potentially think of that to be digital in nature. So now if you really think about a spiking neural network, that effectively has a memory, which is the membrane potential built into it. So it can remember tasks from the past. So effectively, again, a spiking neural network is kind of like an RNN, or a recurrent neural network, which can try to remember the past. It may not have a backward connection, but you can certainly add a backward connection to it. So in other words, it's a simpler version of an RNN or an LSTM, if I may say so.
I see. So it's like in the spiking neural network, like each node, it has like its own internal memory, I guess.
That's correct. That's
Okay.
correct. And that's the membrane potential, which gets updated every time you have inputs which are coming in, which can be in terms of spikes and so on.
Okay.
And so effectively, very much like the standard deep neural networks that you see, except the activation function in this particular case is different. And the network itself, you can potentially think of it as a recurrent network, a simple recurrent network. Training of it is going to be slightly different. You have to consider time into consideration. and quite effective really for sequential tasks. So if your task is more like an image recognition, right, may not be the most effective way of doing it. But if you have videos and where you need to, for example, understand gestures, you want to do optical flow, which are all sequential tasks, turns out these networks can be quite efficient and potentially require less number of parameters
Okay.
to implement.
Okay. So I guess that would be the sort of improvement over like these regular neural networks.
Right. And the application domains could be more the sequential tasks rather than really taking ImageNet and just doing it for ImageNet, which is basically static task.
Okay.
Quite suitable for applications with input sensors like the dynamic vision sensor cameras and so on. These cameras are a little bit different from the regular cameras, which provides, when there's a relative motion between the object and the camera, it produces a spike. So while it captures the timing information, it actually produces spikes which are rare in nature, not too many spikes. And that also leads to potentially developing a hardware that can implement these in an event-driven fashion. Whenever there's a spike, you actually do computation. Otherwise, you don't, right? And hence can be potentially also energy efficient. So a few things suitable for more tasks which are sequential in nature, sequential tasks, and can lead to energy efficiency, provided you have the right kind of hardware to do that.
Okay. So I understand that like, these spiking neural networks, they're like more efficient and so on because their outputs are like a 0 or 1. And like you said before, like it's only when it spikes you do all the computations. But is there like some other property about like some inherent property about spikes that makes it attractive to model? So for example, like is there like a real sort of like neuroscience phenomenon that like actually makes this spiking thing like really good?
Yeah, I mean, it's more bioplausible than, for example, a tan hyperbolic neuron or a even a ReLU, right? So these are more bioplausible. So that's I don't know. We should just use it only for bioplausibility.
Okay.
It has to be a means to an end, and hopefully the means to an end is to be able to do better learning, while at the same time be able to have better energy efficiency.
I see.
Now, if you think about training some of these, neural networks, these spiking neural networks, since we consider time into consideration, right? So back propagation through time becomes important. So it's actually slow.
Oh, I
And
see. So
in a lot of cases, then the question, of course, is, hey, can I, come up with techniques to, more easily train some of these networks? A lot of times we can start with a network which is already trained using the standard ANN methods, and then use, back propagation through time to, reduce the or at least to make it more efficient while not really requiring that much time to train.
I see. Oh yeah, that leads me into another question. So I also saw that your lab, it also did some work in like converting an ANN into a spiking neural network. So would you say like that process is like kind of like similar to regular network pruning in that it's just like an optimization technique to just like compress the size of these models?
Yeah, that's a good question. The initial part of it, I mean, a few years ago when we started looking at spiking networks, there wasn't really a good way of, training such networks. So even though we were really looking at training those networks, we were using, even though we were using static inputs like images, we wanted to sort of have a good way of training. So to that effect, we started with a trained ANN, a standard deep learning, and convert it because the ReLU functionality has similarities with a leaky integrated fire kind of neuron. So we actually took the first step, taking a reasonable network and then made it suitable for a spiking network so that we could have started from scratch with random weights. But that was taking a long, long time, right?
I
The
see.
propagation through time and all. Then also later on, we actually updated it and said, hey, you know something, I'm going to start from there and use threshold and leak as trainable parameters.
Okay.
And to that effect, also, we looked at the possibilities of having a network where the inputs are kind of like what the standard DNN gets, right? The analog inputs. And the first layer of the network could be a spike generator, if that makes any sense.
That would be like the optical flow network?
Yeah, the optical flow networks are different. Those are more sequential tasks. So optical flow networks also, we looked at, somewhat, similar kind of things. But the basic idea was how to effectively or easily train some of these networks for these leaky integrated fire kind of neurons.
Okay. So basically,
and the starting point, if I were to go with a completely random set of weights and train, it was taking a long time. So we wanted to start from a point which was reasonable, and that's where the ANNs came into picture.
Okay. But then if you had enough time and you had enough computational power, could you theoretically have a SNN that had the same performance as a ANN turned to a SNN?
I believe so. But as I keep saying this, that while we can get the same performance as an ANN for static tasks, it's possible. Training becomes difficult, but it's possible. But that's not the right application.
Okay.
The application, I would say the right applications would be more sequential tasks.
Okay. Yeah.
Where you're trying to replace, for example, an RNN or an LSTM, which are usually more expensive.
Yeah.
So it's one can potentially think it's a simpler version or a poor man's version of an LSTM. The leak sort of acts as a forget gate in some ways.
Okay. So, you've talked a lot about like how these SNNs, they're like, they're kind of like you said, like a poor man's LSTM, but then they're also like very efficient and so on. So how come these networks aren't like being widely used right now? Is there like some sort of like, giant hurdle that must be passed first?
Very good question. Very good question. Again, you have to keep in mind the applications which are going to be suitable for SNNs. That's one. The second thing is that, training is difficult. So to that effect, for example, in our group, we've been looking at things like, can I have hybrid networks? Meaning thereby part of the network could be ANN, part of the network could be SNN. SNN to capture the temporal information, SNN to actually make my training easier in some ways. So we've been looking at hybrid networks. That's one of the things. The third aspects of it is that today's GPUs that you have are not quite suitable for SNNs. SNNs ideally would I would like to have, for example, event-driven computation to take effectively the energy efficiency that I'd like to get. So to that effect, there are commercial hardwares are not quite available, but hardware like Loihi from Intel, I don't know if you've heard of that. It's not a commercial hardware. It's still in the experimental stages. And a few years ago, there was this True North. They were all for spiking networks. And the basic idea in Loihi and these kind of not in the commercial world yet. The basic idea is to really do these computations in an event-driven fashion, and to be able to take advantage of SNNs to really implement something which can be really power efficient, energy efficient. while still being able to learn, the sequential information that I'm talking about.
Okay.
So
Okay.
that's a big hurdle. And the hurdle is also training. The training takes more time.
Okay. So, going back to your point about like these hybrid SNN, like ANN networks, or I guess like or regular networks. So would it be something like let's say I have a regular CNN LSTM. So I would just like keep the CNN and then I would just replace the LSTM with like a spiking neural network or something.
Well, it could be the other way around. It could be that you have a simple, LSTM,
Okay.
and then you follow it up with an SNN to
Mhm.
capture more of, the sequential information. Or it could be potentially, let's think about the scenario that you have a drone that you'd like to take from point A to point B.
Mhm.
And you'd like to do all your computations on board rather than going to the cloud and trying to have decisions from the cloud.
Okay.
So think about that you'd like to implement a low complexity network. And let's assume that you're going to do completely vision-based navigation.
Mhm.
Now, for that, you need to do optical flow. You need to do depth estimation. You need to do localization. You need to do object tracking, right?
Mhm.
And then dodging objects. So all these different functions that you need to do, right? And let's say that you have sensors and you're in a GPS devoid environment. So you're only doing with vision sensors. And the
Okay.
vision sensors could be, for example, the standard frame-based camera and the
Mhm.
DVS camera that I just talked about, right? The dynamic vision sensor kind of cameras.
Yeah, yeah, yeah.
So now if you take these two inputs, right, and you can use both the frames and the spike-based inputs coming from the DVS cameras,
Mhm.
right, combine them together, part of the processing can be done in an ANN,
Mhm.
part of the processing can be done in SNNs, which would take spike inputs directly from these DVS cameras, capture the timing information well. And
Mhm.
for better object detection, sometimes you might actually be able to use the ANN part of it, combine them together into a network, which is a hybrid network, to do
Mhm.
optical flow.
Okay.
Or to do, for example, segmentation.
Okay.
And the training also becomes simpler because you're
Mhm.
taking part of it to be ANN, part of it to be SNNs,
Mhm.
and taking advantage of both worlds. You can actually, for example, think of networks and the hardware architecture potentially that can handle both ANNs and SNNs efficiently. Does it make sense?
Yeah, yeah.
And training becomes simpler too. Or you can potentially think of part of the network being SNN, part of the network being ANN. So these networks can be in parallel,
Mhm.
or it can be merged together in some ways. Yeah? The most important thing then becomes, hey, how do I take the ANN, SNN outputs, combine them into an ANN network. So those things, the interfaces that you have to think about, and that can be done.
Okay. Okay, so at this point of the interview, I was like, I'm just gonna like try to ask more hardware related questions as opposed to purely, I guess, like machine learning. So, previously you mentioned your DVS camera. So I do know that it's like a sort of like neuroscience inspired, but can you explain a little bit more about like how it works, how it is neuroscience inspired?
Yeah. So one of the things is that these cameras are the good thing about these cameras are that if you think about if you keep a camera and there's no motion right in
Mhm.
front of that camera, then there'll be no spikes generated. So
Okay.
that really means that you don't need to do any computation. Now think of the fact that I have some movements, some objects are moving.
Hmm.
So if these objects are moving and there's a relative motion between the camera and the object,
Hmm.
then the pixels which are moving either in the positive direction or in the negative direction, I can provide an output. And that output is either going to be a positive spike or a negative spike.
I see.
Okay. And that spike information now can be used directly by your, let's say, spiking network. Now,
Okay.
why that is also important is to realize that there's a timing difference between the spikes that are going to be coming out,
Hmm.
right? And if I can capture that time differences and the movements of the spikes, then I can effectively do, very good optical flow.
I see.
Now think about it this way: optical flow is a very complex problem. I can now do what we're trying to do today, is what we're calling object flow. And that might be more important when the drones are flying. As an example, I need to find out my objects which are moving. And my attentions can really be on the objects that are moving only.
Wait, so are these like DVS cameras? Are they basically sort of like, well, they're not like exactly the same thing, but instead of like RGB cameras, they're sort of like edge detectors? So,
Not quite edge detection, but edge detection can be also included in the sensor if you want to.
okay.
Okay. Now there's a effort from our lab also trying to put edge detectors in the sensor itself.
Okay.
Okay, so that the sensor output is a rich output that you can effectively use directly. But in this particular case, it's actually providing spike inputs, and the timing between the spikes are quite important to be able to track objects which are moving fast, moving slow, moving in some complicated ways, and so
on. Okay. Okay, so in like a large part of your talks.
So just to add to it, now we can, using this, we're able to track objects, right?
Okay.
So doing tracking of multiple objects using such an approach.
Okay. And I guess
in fact, interestingly enough, using such an approach, what we have some demonstrations in our lab is to show that I can track objects which are going at different speeds. So it said, hey, I'm interested in finding out cars which are moving at above 60 miles per hour. Okay, so that I can track only those objects which are going at larger than 60 miles per hour, as an example. When one can do that using these networks very effectively, and with simple networks, it can track. So you can say, hey, objects moving between 30 miles per hour and 40 miles per hour is what I'm interested in. I'm not interested in something else. So it's possible to do that.
Oh, I see. Okay, so
we can track those things separately.
So I guess like right now, like the sort of object detection networks, I guess like that go across time, that would be much more energy not efficient, because you have to like take those large RGB images and across time, and then you have to like analyze one chunk at a time. But I guess this spiking neural network, because it has like that internal memory, and because your video is like from that custom neuro whatever.
Other sensors, custom sensors.
Yeah. It just sort of like compresses that information down to something a little bit more basic.
Yes, and one can do tracking and all quite easily.
Okay, that's really cool. So a large part of your other talks, your previous talks, you talk a lot about like hardware. Can you explain a little bit more about why you would want to create a custom AI like hardware for SNNs, as opposed to maybe just slapping a SNN on a regular GPU or something?
Yeah, I mean, any programmable network can really be used for doing inference, right? Programmable hardware, so to say. You can do it in FPGAs, or you can do it in GPUs, or you can do it in CPUs, and so on, right? But if your algorithm matches the hardware, that's when you get the efficiency, the most efficiency, right? Now, if they don't, then you don't have it. Now, SNNs, as an example, have this sparse inputs that are coming in. And if I have a lot of sparse inputs which are coming in, and if I can do computations which are based on events being some of these spikes when they come in, else I'm going to turn it off, that gives me an advantage, right? Because then I don't have to do computations all the time. The second thing is that sparsity also comes because of this leaky integer and fire neuron, they fire at only certain times. So I'm going to only do computations at when the output spikes are generated. So the third thing that is also important is a lot of these computations are accumulations, right? Or matrix vector multiplication. In case of SNNs, is accumulation. In case of ANNs, it's basically the matrix vector multiplication. So if I can now do matrix vector multiplication or these accumulation functions that I'm talking about, right, in the memory itself, rather than fetching data from the memory, going to the CPU, doing computations and bringing it back to the memory itself, right? If I can do these computations in the memory itself, then I can actually increase my efficiency a lot. So you might have heard of the memory wall that people talk about. A lot of, inefficiency comes from really taking data from the memory, bringing it to the CPU and back it to the memory again. Okay.
Yeah.
So instead of that, if I can do computations in the memory itself, that would be quite efficient. So that's another thing that we're trying to do. Some of these computations in the memory itself. For example, if you think of the brain as a simple example, I don't have a CPU on one side and a memory on the other side.
Yeah.
It's all mixed together. So now what we're really talking about is that, hey, can I have these computations all mixed together in some ways so that I do some of these, power-hungry computations in the memory itself, rather than getting data from the memory and bringing it back.
Okay.
And that being really a major component of the total power consumption or the energy consumption. So can I do that? Then I can make it more efficient. So those are the different things that we are also looking at for the hardware to have, so that I can do efficient computations in the memory, do event-driven computation, and then at the end of it, reduce some of these interfaces between the analog to the digital domain to be able to do more efficient hardware, well suited for the kind of algorithms that are being developed, the machine learning algorithms, be it spiking or non-spiking.
Okay. So when you were, and this is going to be like my final question. So when you were like mentioning how the memory is like, it's not like separate from the CPU, right? That was like referring to the von Neumann architecture. So I do know that the von Neumann architecture, it was loosely based off of neuroscience. Like, I guess like the guy thought that, memory, I mean, we do have memory and we do have a sort of CPU. And I guess like you try to like, sort of like loosely combine those things. So my final question is, which areas of neuroscience should we sort of like really focus on so that we can like combine it into like these AI inspired hardware? Like, which is the most promising area?
Yeah, again, a good question. At one time, when these computers were developed, people thought that, hey, we can be doing brain-like functions. And as we learn more and go more towards bioplausibility, and again, we find that, hey, we probably have to do better than what we did earlier. In fact, even the Boolean logic, when it was initially developed, the idea was to do computations like the brain. And then going forward with the von Neumann architecture, but we certainly know that the computations in the brain are certainly all, in some ways we don't understand it, but certainly we don't have a separate processing unit and a separate memory in some form. Now, while we could do computations very effectively with von Neumann architecture, it's a very programmable and versatile architecture. While we could do these computations very effectively, but with the change in workloads and large workloads and so on, it turns out that energy consumption has gone through the roof, right? And power consumption, energy consumption has gone through the roof. So the question, of course, is, hey, can I take some cues from the brain, or can I really look at what the inefficiencies of the von Neumann architectures are? And then if you really try to analyze it, it finds that, hey, the data movement costs are humongous, right? The data movement from the memory to the CPU and back and so on. So is it possible that I can get rid of that or alleviate that cost? And to that effect, if I'm able to do some of the core computations for AI, as an example, in the memory itself, then I can potentially reduce that cost. And it turns out that this matrix vector multiplication is very well suited to be able to be done in the memory itself. And this is something which is important and being really required a lot in most of machine learning applications.
Okay.
So that's why, you know, it's still not what exactly the brain does.
Mhm.
Okay. But it's sort of like, I'm trying to take the memory wall bottleneck that
Mhm.
von Neumann computing has and alleviate that to a problem which is, you know, uh, of doing the computations in the memory itself. And how do you do that? Is it an effective way of doing it? And is the architecture that I'm going to be developing with such in-memory computing capabilities
Mhm.
can be better than today's von Neumann architecture for these machine learning applications.
Okay. Thank you for allowing me to interview you.
All right. Thank you.
Okay.